All right, so you should have done the calculations. I have them hidden behind the screen. So hopefully you have this done correctly. We'll just go through it relatively quickly. First, for the ice, the specific heat was 2.10 joules per gram degree Celsius. We multiply that by the mass of 454 grams times the change in temperature, which was going from negative 20 up to the melting point. Remember that the melting point of water is 0 degrees Celsius. So the delta T is not from negative 20 all the way to the top. It's each of the little segments of our heating cooling curve graph. So when we multiply those three values, you get 19,068 joules. For this problem, I'm just writing down everything that's in my calculator. I will add them all up and I will round it one time at the very end. So the amount of energy for ice is 19,000 joules. The second part was just to melt it. We took the heat of fusion, which was 334 joules per gram, multiplied by the 454 grams, and we get 151,636 joules. Then, to heat up the water. Heating up the water takes a lot of energy. It had to go from 0 to 100 degrees, so our change in temperature is 100 degrees Celsius. So we took the 4.18 times 454 times 100, and you get 189,772 joules. So again, so far through all this, great, that's kind of a lot of energy, but watch what happens when we go to boil it. Boiling water requires a lot of energy. It requires over 1,000,000 joules of energy. So it's the 2,260 joules per gram times the 454 grams. When you multiply those values, you get 1,026,040 joules. And again, I'm just writing down everything in my calculator. I'll round it once at the very, very end. That's a lot of energy to boil water. Once we turn it into steam, it doesn't take quite as much energy to heat it up. And then it's 23,608 for that. And all told, to find out all 5 steps, we have to add them together. It's 1,410,124 joules, or we could round that into kilojoules. Remember, the prefix kilo means 1,000. This would be 1,410 kilojoules. And so on Moodle, we would just round it to 1410 and put a kilojoules in. Or if it specifically asked for the number of joules, we could go ahead and put just the J for joules and just write the whole number out. Don't worry about rounding this each and every time because it might mess you up. Calculating energy requires you to think about what's going on that heating or cooling curve. So if we went back to that heating cooling curve, this graph is going to be similar for every substance in the universe. This graph is going to be a melting, a heating, and a boiling for all the different substances, depending upon what the specific heat of the sample of ice, of the solid is, the specific heat of the liquid, the specific heat of the gas. That will control the slopes of those lines. The heat of fusion and the heat of vaporization will control the length of these lines. So again, showing this was a lot of energy. It actually is not drawn to scale because this was like 1,000,000 and this was in the 100,000. So again, if you're talking about what we're looking at here, we're looking at how much energy did it take to go from 0 degrees liquid to 100 degrees liquid. That amount in our graph was 189,772 joules. And then the other part of the graph, the other part of the graph, this was 1,000,000. So this needed to be like 5 times longer than this. If we had drawn this to scale, we would have gone way off the page over there, like on the periodic table, like in my classroom, you know what I'm talking about. So it would have been a lot more energy. And again, all we're looking at is what's taking place here. So again, for the first phase, as we went from solid up to the melting point, we did that. Once we began to melt it, we had to put more energy in, and it began to melt. And then if we were to keep going for the next part to turn it into a liquid, more energy goes in, more energy goes in, and as a liquid, we would have had some thermal energy, and then it would have been a liquid, would have looked like this. So that would be what it looks like as warm water. And as we cause it to boil, all of this energy that keeps going in is going to cause the phase diagram to change. The temperature won't be changing once it's at 100 degrees. So there we have our thermals are the same, and now the phase energy is changing. This is just kind of understanding how energy is required to make something change. You're either going to change the temperature or you're going to change the phase. As you put energy into your system, you're either causing the temperature to go up or you're causing the phase of that sample to be changed from solid to liquid or liquid to gas. Remember, to go from a liquid to a gas, that's going to require a lot more energy than just melting does. I hope this video is making a little bit of sense, and I hope that you understand how to do these calculations, because you have a couple of assignments that you'll need to work on about how to calculate the amount of energy required.